In this video, we will present the frequency representation of a random process. And to do this, we will introduce the power spectral density function. A random process can be seen as a set of signals. We have a signal associated to every possible outcome of a random experiment. And for all these signals, it's possible to obtain the Fourier transform. But maybe, because we have an infinite integral in the definition of the Fourier transform, maybe some of these signals have not defined a Fourier transform. To overcome this potential drawback, it's possible to define the truncated signals with a given duration capital T or uppercase T. We truncate the signals from minus this length, minus T divided by 2, to T divided by 2. And in this case, the definition of the Fourier transform will have finite support integrals. Because now the integrals are between minus t halves and t halves. With the definition of the truncated random process with a given duration capital T, it is possible to compute the Fourier transform for every signal, and from this Fourier transform, the square modulus of the Fourier transform is the spectral energy divided by T. Spectral energy per unit time is the spectral power, and the power spectral density of random process X is just the mathematical expectation of this spectral power when the duration of the truncated signals goes to infinity. Taking into account the linearity of the mathematical expectation and the limit, we can have this alternative expression. The ratio between the mathematical expectation of a square modulus of the Fourier transform of the truncated process divided by T when T goes to infinity. From this definition, taking into account that here we have a square modulus of a frequency response, we have a very simple implication. A power spectral density is a non-negative function. To compute the power spectral density from this definition in general can be difficult. However, the power spectral density is related with the autocorrelation function of a random process. And the Wiener-Khinchin theorem states how to compute the power spectral density from the autocorrelation function. If this autocorrelation function satisfies some conditions, basically it's a function that doesn't go to infinity for every time instance, mathematically, if for every interval a of duration tau, we have a finite integral of the autocorrelation function, the power spectral density can be obtained as the Fourier transform of the time average of the autocorrelation function. The Wiener-Khinchin theorem has a couple of corollaries for stationary and for cyclostationary random processes. For stationary random processes, if the autocorrelation function is well defined, we don't have infinite values, the power spectral density is just equal to the Fourier transform of the autocorrelation function. This is straightforward because the time average of the autocorrelation function is itself, because the autocorrelation function doesn't depend on the time for a stationary random process. In the case of cyclostationary random processes, as well as the autocorrelation function doesn't go to infinity, the power spectral density is equal to the Fourier transform of the time average of the autocorrelation function in a single period, because being a periodical expression of the time, in this case for cyclostationary random processes, the time average is equal to the time average in a single period. The power spectral density is providing information about how the power is distributed in the different frequencies, and it is related with the power of a random process. The power of any random process can be obtained by integrating the power spectral density. Taking into account the properties of the Fourier transform, to integrate in one domain is equivalent to evaluate at zero in the other domain. This means that the power for a stationary random process is equal to the evaluation of the autocorrelation at zero, and that the power for a cyclostationary random process is equivalent to the value of the time average in one period of the autocorrelation function at separation tau equal to zero.